All right. I'm going to be reading from the Jeppsen Private Pilot Test Guide. Let me share that screen. Okay, we're going to be looking at the Private Pilot Test Guide from Jeppsen, and I recommend that that you read through the chapter just to get a familiarity with it, but then really spend most of your time on this book. So I'm going to look at Section A, the four forces of flight, and Section B, stability, and Section C, aerodynamics of maneuvering flight. So we'll look at all three of these and just run through it, and hopefully it'll be helpful for you to run through it as well from the recording. So Section A, four forces of flight, forces acting on an airplane. The four forces that act on an airplane are lift, weight, thrust, and drag. So that's, up and down, back and forth. So lift is up, weight is down, thrust is forward, drag is backward, holding it that way. The forces are in equilibrium when the plane is in unaccelerated flight. In other words, they equal each other. The up forces and the down forces are equal. The forward forces and the back forces are equal. And so the plane's just moving along. During straight and level flight, lift equals weight, thrust equals drag. This is also true during climbs and descents and any time the airplane is not accelerating. Lift, the upward motion or the upward force. The plane's wing shape is designed to take advantage of Newton's laws and Bernoulli's principle. Bernoulli's principle states that as the velocity of a fluid, including air, increases, its pressure decreases. This principle provides an explanation of lift produced by an airfoil that is curved more on the top than on the bottom. Air travels faster over the curved upper surface, causing lower pressure on the top surface. The airflow pattern around the wing causes a downward flow of air behind the wing, called downwash. The reaction to this downwash results in an upward force on the wing, demonstrating Newton's third law of motion. The angle of attack is the angle between the wing chord line and the relative wind. So you have your wing chord line, and that's just like, your wing is like it's kind of shaped like a teardrop or something like that, and so the chord line that's at the center of the wing is like that, and then the direction of travel is like that, and so this angle is the angle of attack. It's covered really well in the actual book. So the angle of attack is the angle between the wing chord line and the relative wind. And I said direction of flight, but that's the wind. The wind's coming from your direction of flight. Total lift depends on the combined effects of airspeed and angle of attack. When speed decreases, you must increase the angle of attack to maintain the same amount of lift. And you know that. You get to slow flight, you've got to lift the nose of the airplane, and the outside picture changes because you had to do that to keep the plane from to decreasing in altitude. Angle of incidence refers to the angle between the wing chord line and the line parallel to the longitudinal axis of the airplane. So that's angle of incidence, which makes sense, I hope. A stall is caused by a separation of airflow from the wing's upper surface for a given airplane. A stall always occurs at the critical angle of attack, regardless of airspeed, flight altitude, or weight. In other words, one of the questions has to do with weight and stalling. It's going to be the same. It occurs at the critical angle of attack. That determines the stall. Flaps enable steeper approaches to a landing without increasing speed, because you know that when you put the nose down, your speed increases. And when you're going to land, you want the speed to decrease until you land. And so applying flaps allows you to make that happen. Ground effect is a result of the interference of the surface of the earth and the airflow patterns around an airplane. Ground effect reduces induced drag on the airplane and increasing performance. It increases the performance of the airplane, flies better under ground effect. An adverse consequence of ground effect is that the airplane can become airborne before reaching the recommended takeoff speed, but then be unable to climb out of ground effect. So when the plane rotates, you could climb right then about 60 miles an hour with the Cherokee, but you couldn't sustain that. So that's one reason we rotate at 60. We wait till we get to 75 or 80, and then we begin to climb at that speed, because that's a speed that we can actually sustain a climb. But at first, airspeed comes alive at 40, rotate at 60, and then begin to climb at 75 or 80, whatever, whatever seems right. Just don't want to run out of runway. Let's see, ground effect. Another undesirable consequence of ground effect is that any excess speed at the point of flare can cause considerable floating. So if you have ground effect and you're coming into land and you're too fast, ground effect is just going to let you float down the runway. And you might have to do a go around if you can't get down quick enough before you run out of runway. So that's the description of section A, and you can follow along in your own book, etc. And I encourage you to do so and make marks of things that look important to you or whatever. And then the rest of this next few pages has to do with questions. And pretty much, I'm going to read the question and the correct answer. I don't care about the wrong answers. Okay. The four forces acting on an airplane in flight are A, lift, weight, thrust, and drag. And you already know that. So if you have your, airplane, here, and there's the tail and the wings, you have thrust going that way, drag going that way, weight going down, and lift going up. And so you pretty much have an idea of that, I'm sure. Lift is the upward force created by the airflow over and under the wings. Weight, caused by the downward pull of gravity, opposes lift. Thrust is the forward force that propels the airplane forward, and drag is the retarding force that opposes thrust. There's way more to go on that, but that's good enough for what we're studying. What are the four forces that act on an airplane in equilibrium? Well, we already know what it is. It's answer A. Oh, sorry, I didn't read it very carefully. When are the four forces that act on an airplane in equilibrium? When are they equal? Answer A. In straight and level unaccelerated flight, the four forces are in equilibrium. Lift equals weight and thrust equals drag. And I really don't want to have the answer here because I like to review without having the answer there. Because they make a little thing that you can use to cover up the answers if you want. It's here, and you can use this to cover up the answers for your study. And I just used my hand for the most part. I didn't use this, obviously, because I just now tore it out. But you can use this to, to go down and reveal the answers in a way that may help you study. So this is figure 3.3. Refer to figure 1. The acute angle of attack. The acute angle A is the angle of attack. And so that's B. The angle between the chord line and the relative wind is the angle of attack. You can go look at figure 1 and get some more insight. The term angle of attack is defined as the angle between the A, the chord line of the wing, and the relative wind. The angle of attack is the angle between the chord line and the wing and the relative wind. The other answers are wrong because the angle of attack is not measured from parts of the airplane other than the wing. So that's important. That's where you get angle of attack. It has to do with the wing. Okay, so this last question, for some reason, I can't get to it. Goes all the way down. There we go. Is that 3.5? Yeah, that's the last one. The angle between the chord line of an airfoil and the relative wind is known as the angle of B, angle of attack. So we just get a bunch of questions about the same thing. You're going to get that. It's going to be on the test. One of these questions will be on your test. Angle of attack is the angle between the wing chord line and the relative wind. Angle of incidence refers to the angle between the wing chord line and the line parallel to the longitudinal axis of the airplane. The wing is usually attached to the fuselage with the chord line inclined upward at a slight angle. And that has to do with how the plane's going to sit while you fly. I mean, you wouldn't want the angle of incidence where at normal flight, your cockpit is facing down. That would be uncomfortable. You don't want it facing too high. You'd like it to be pretty level. So that's basically what we have, and we know where to put the line of the cockpit to climb or have level flight or descend. All right. What is the relationship of lift, drag, thrust, and weight when the airplane is in straight and level flight? Let's answer C. Lift equals weight and thrust equals drag. It's, straight and level flight. It's just another, they're just asking these questions in different ways. Same concept. One of the main functions of flaps during approach and landing is to C, increase the angle of descent without increasing the airspace. Because normally you when you put the nose down, your speed's going to increase. With enough flaps, that doesn't happen that way. You're able to actually maintain a decent speed, which is going to make you descend. And, hopefully, what is it, like 70, 75 is a really good. I mean, anything below 80, I think, is well, not too far below 80, but at any rate, number 3-8, what is one purpose of wing flaps? Answer C, to enable the pilot to make steeper approaches to landing without increasing airspeed. 3-9, well, that's what this is. Flaps increase both lift and drag, enabling a steeper approach without increasing airspeed. Trim controls, not flaps, relieve the pilot of maintaining continuous pressure on the controls. Some types of flaps increase wing area when deployed to increase lift. So yeah, it's nice to use the trim on landing. Pretty much just put it all the way back when you want to try. I mean, I tried that last couple of times I landed, and it was helpful just to give all the trim all the way back to land. Maybe that won't always work, and maybe I shouldn't be doing that. I'm not sure, but it worked last time I flew. Okay, 3-9. The angle of attack at which an airplane wing stalls is C. Remains the same regardless of gross weight. Some of these others are kind of halfway true. Who cares? What they're looking for is the angle of attack which the airplane wing stalls is the same regardless of gross weight. The critical angle of attack at which an airplane stalls is determined by the lift coefficient of a particular wing configuration. An airplane stalls when the critical angle of attack is exceeded regardless of weight and airspeed. Sorry about that. And number 10, what is ground effect? A, it's a result of the interference of the surface of the earth with the airflow patterns around the airplane. And that's what it is. The surface of the earth makes the airflow patterns a little different, and it makes the wing float. There's a lot of physics. There's a lot of physics and stuff that go through that. What you're hearing is my radio. I'm at, I have a day, I can take some time to do this, but I'm at, school, and that's the radio. But it's a teacher work day. So the next one, 3-11, floating caused by the phenomenon of ground effect is most realized during an approach to land when at B, less than the length of the wingspan above the surface. So what's the wingspan? It's about, 38 feet, something like that. And I'd have to look in the book. But whatever the wingspan is, once you get lower than that, then you begin to get in ground effect, and the plane's going to fly a little better than it otherwise would. 3-12, what must a pilot be aware of as a result of ground effect? Answer is B, induced drag decreases, therefore any excess of the point of flare may cause considerable floating. So you get on there and you flare, and you're going too fast, you're just going to keep going. You're not going to float down, you're going to float across. So that's the issue of ground effect. Okay, got a few more questions here. So 3-13, ground effect is most likely to result in which problem? B, becoming airborne before reaching recommended takeoff speed. So that could happen. If you just pull back on the yoke too much as you're taking off, you're going to get airborne, and you're not going to be able to sustain it. Once you get out of ground effect, kind of fall back down, blah, blah, blah. So it's not a good situation to be in. You want to make sure you don't really try to fly the plane until the plane is at flying speed, which is 75 or 80, and then pitch for whatever we pitch for, 85 or something like that. Okay, which statement, 3-14, which statement relates to Bernoulli's principle? The answer is C, air traveling faster over the curved upper surface of an airfoil causes lower pressure on the top surface. Bernoulli's principle states that as the velocity of a fluid, including air, increases, its pressure decreases. The explanation of lift that relates to Bernoulli focused on higher velocity of air over the upper surface of an airfoil. The other two answers are also valid explanations for lift, but are related to Newton's third law of motion rather than Bernoulli's principle. So this is a little tricky. Just keep in mind that, when you have an airfoil like this, your wing, and this is more flat, and so the wind approaches, and some of it goes here, and it's take a longer trip, and the air that goes here is a shorter trip, and so that pulls the wing upward, which is lift. Okay, number 315, changes in the center of pressure of a wing affect an aircraft's seat, aerodynamic balance, and controllability. So the center of pressure of a wing. So if your wing, there's your wing. I tried to draw it flat here, more of an airfoil type thing. So you want the aerodynamic balance. Here's the center of lift. Say that's the center of lift. If your aerodynamic balance, I think, is supposed to be just a little behind that. I don't remember exactly. We're going to cover that in a minute. Anyway, if that's too far back, the plane isn't going to fly good. If it's too far forward, it's not going to fly good. It's not going to be balanced. So you want it to be fairly balanced. And I don't remember if it's a little forward or a little back. We'll get to there in a minute, though. But anyway, the aerodynamic balance and controllability is affected by changes in the center of pressure of a wing, the center of where the lift is. I know they say center of pressure. All right, section B. So we've been going, I can't tell how far we've been going. Oh, well, shouldn't take too long. Section B, stability. Stability characteristics. An airplane cannot be completely stable or would not be possible to maneuver it. However, some stability is needed for desirable handling characteristics. Another item, an aircraft that is inherently stable requires less effort to control. Sure, it flies well. Longitudinal stability involves the pitching motion or tendency of the airplane to move about its lateral axis. So you have your airplane, and so this is a terrible airplane, I suppose. And there's your propeller, and here's the back of the plane, and of course you have a rudder. And so a line through the center of the plane is the lateral line through the plane. So the plane can rotate around the axis that way. It can rotate around the axis over the axis like that. It can just do different things around the axis. It can go up and down. Anyway, it's rotating about that axis. So longitudinal stability involves the pitching motion or tendency of the airplane to move about its lateral axis. Location of center of gravity. So you have a plane, and if you put something under it and balance the plane, where the plane balances is the center of gravity. The location of the CG with respect to the center of lift determines the longitudinal stability of the airplane. The airplane is more stable when CG is forward of CL. In other words, the CL, that's the lift. So CG is a little ahead. So I had it backwards a while ago. So you want so if you have your wing here, and you have your center of lift here, CL, and so we want CG to be just a little forward of that. So this is your CG right about here, CG. So CG is just a little ahead of the center of lift. All will be well, or more stable, etc. So looks like we're doing good over there. Okay. Loading an aircraft to the most aft CG causes the airplane to be less stable at all speeds. Well, of course, put a bunch of weight back here, the tail's going to go down. It's not going to be stable at all speeds. An airplane loaded with the CG aft or to back of the approved CG range is difficult to recover from a stall condition. Well, of course, the plane begins to go down in the back, and so you try to use the rudder to bring it up, and the rudder isn't powerful enough to overcome this incorrect loading of the airplane. Stalls. The inherent ability of an airplane is important because it relates to the aircraft's ability to avoid stalls and spins. Familiarization with the causes and effects of stalls is especially important during flight at slow airspeeds, such as during takeoff and landing, where the margin above the stall speed is small. That's where you have a lot of risk. When you reduce power without adjusting the controls, an airplane pitches nose down because the downwash of the elevator from the propeller airstream or slipstream is reduced, which reduces elevator effectiveness. So that makes sense. You got a lot of wind coming in the airplane here from the propeller, and that wind is going over the elevator. The elevator has a certain adjustment it's been made to keep the plane, level flight or whatever kind of flight you want at the time. And when you reduce how many times the propeller is turning around, you're reducing the wind on the elevator. And so this is less effective. And so when it's less effective, the nose pitches down. And that's what this is talking about. Spins. You must stall an airplane before it can spin. During a spin, both wings are stalled, but one wing is more stalled than the other. This one I struggle with. I really had to read this a bunch of times before I could get it on the test. Because, yeah, one wing's more stalled than the other, but they're both stalled. That's important. Question 3-16. Can I get it up there? Not very well, can I? There we go. An airplane is said to be inherently stable. C. Requires less effort to control. Let's see if we can read that better. An airplane, it should be, is said to be inherently stable. Requires less effort to control. Anyway, so that's the deal. If it's stable, it doesn't require a lot of effort to control it. What determines the longitudinal stability of an airplane? Answer is A, the location of the center of gravity, or CG, with respect to the center of lift, which is, the CL. 3-18, what causes an airplane except a T-tail to pitch nose down when the power is reduced and controls are not adjusted? And his answer is B, the downwash on the elevator from the propeller slipstream is reduced and the elevator effectiveness is reduced. So a T-tail airplane, so if you have a side view of an airplane, so here's your airplane like this, and here's your elevator and your rudder and your wings like this, etc. Well, a T-tail has the elevator is up here instead of being down here. It's just raised up. So it's a little different. I have no idea what it's like to fly one of those. At higher propeller settings in airplanes other than T-tail designs, the propeller slipstream causes a greater downward force on the horizontal stabilizer. When power is reduced, its downward force on the tail is also reduced, and the nose pitches down. 3-19. An airplane has been loaded in such a manner that the CG, or center of gravity, is located aft of the CG limit. In other words, you have a chart that shows where the CG can be located in the plane. One undesirable flight characteristic of a pilot might experience with this airplane would be B, difficulty in recovering from a stalled condition. You try it, and it doesn't work. You don't have enough power to overcome the stall, which you're going to have a bad day. Okay, so number 3-20 is loading an airplane to the most aft CG causes the airplane to be A, less stable at all speeds. It's not as stable. It's harder to control. Things don't work the way you expect. 3-21, in what flight condition must an aircraft be placed in order to spin? Well, we already know that. It's number C, stalled. You got to stall it in order to be able to spin it. An airplane must be stalled before it can spin. The spin progresses when one wing becomes more stalled than the other, which leads to rotation. A steep diving spiral is different than a spin because the airplane is not stalled, even though it is descending and turning. So there's, different ways to spin the airplane, which is kind of cool. 3-22, during a spin to the left, which wings are stalled? Of course, it has S. Should be which wing is stalled, whatever. They're trying to trick us. We know the answer. It's A. Both wings are stalled. So that's what it is. In any spin, both wings are stalled, but in a spin to the left wing is more stalled. And that's not what they asked. Section C, last section for Chapter 3. Aerodynamics of maneuvering flight. Left turning tendency. Well, we all know you take off the plane, it wants to turn to the left. So this explains some of that. In addition to the basic aerodynamic forces present on a climb, a combination of physical and aerodynamic forces can contribute to a left-turning tendency in a propeller-driven airplane. or in propeller-driven airplanes. These forces are 1, 2, 3, 4, 4 of them. Torque. The clockwise action of a spinning propeller causes a torque reaction which tends to rotate the airplane counterclockwise about its longitudinal axis. Torque is explained by Newton's third law of motion. For every action, there is an equal and opposite reaction. And item 2 here, it is greatest at low air speeds, high power settings, and high angle of attack. Well, when does that happen? When we're taking off. This plane's going slow. We've got maxed out throttle, and we're trying to climb the airplane, up to fly. The next item, spiraling slipstream. As the propeller turns the air, the air rotates around the airplane and produces a backward flow of air, a slipstream, wrapping around the airplane and striking the left side of the vertical fin. Even though this has been disproven, it's still going to be in the test, and you're going to have to answer it this way, even though there's things that show that this isn't anything to be concerned about. You still have to have it. Gyroscopic precession. Propeller exhibits characteristics similar to a gyroscope, rigidity in space, and precession. The reaction to a force applied to a gyro acts in the direction of rotation and approximately 90 degrees ahead of the point where the force is applied. You play with gyroscopes. You know how it works. You have a gyroscope spinning. You turn it to the left, and it wants to go up, or you turn it to the down, and it wants to go to the right. Whatever. It's about 90 degrees off. Well, it is 90 degrees approximately. The next item, asymmetric thruster P factor. This is a very powerful aspect of the left turning tendency of the airplane. The propeller blade descending on the right produces more thrust than the ascending blade on the left. So you have your, you have your airplane right here. Here's your tail and rudder, and here's your wings, and then your prop. So the prop is going down over here and going up over there, and so when it goes down, it produces more power than when it's going up, produces less power, which makes the plane want to turn to the left because it's weaker on this side and stronger over here. The stronger wants to push against the weak. This is the most prominent of the left-turning tendencies, and it is most pronounced at low airspeed, high power, and high angles of attack. In other words, when you're taking off, or any other time that you would have that same situation. The horizontal component of lift is what makes an airplane turn. That's important to know because it's not intuitive. So the horizontal component. So when you have an airplane that is banking, if I can draw an airplane here that is banking, the tail is up, the rudder's pointed that way, the wings are like that, and here's your propeller, and we're banking at say 30 degrees, so that our level flight was here, and now we've made it turn up like that, about 30 degrees, whatever, and that's one of the ways we turn, and so we have vectors that are vertical and vectors that are horizontal, and it's the horizontal vector of flight that makes the airplane turn. Next thing, load factor is the ratio of the load supported by the airplane's wings to the actual weight of the aircraft and its contents. That's the load factor. I have trouble with that definition. I have to read it several times to understand it. The load factor is the ratio of the load supported by the airplane's wings to the actual weight of the aircraft and its contents. And number 3 here, turns increase the load factor on an airplane as compared to straight and level flight. And there's a chart we're going to look at that shows that when you're at a 30 degree bank, you have to multiply the weight of the aircraft, I think times like 1.154. And when you do that, it's going to show you that your weight increases. And I think when you're at a different bank, I don't know, it was 30 or 60. Anyway, we'll get to that. You just have to multiply by a factor that tells you what the load factor is. And it can get pretty high pretty quick and cause trouble if you're not careful. Third point here, the amount of excess load that can be imposed on an airplane depends on its speed. Yes. At 60 degrees of bank, 2 Gs are required. Nice. So you have to multiply the weight of the aircraft times 2. So a 3,000-pound airplane all of a sudden weighs 6,000 pounds. To determine how much weight the airplane's wing structure must support, multiply the airplane's weight by the number of Gs. So we have a chart that shows the number of Gs at different angles of attack or whatever, different turn angles. An increased load factor, whether it is experienced in a turn or by pull-up out of a descent, causes an airplane to stall at a higher airspeed. That's important because you could be going fast and think there's no way you're going to stall. All of a sudden, the airplane stalls. It's completely unexpected. 3-23. Okay, so here is question 3-23. In what flight condition should be conditions? In what flight conditions are torque effects more pronounced in a single engine airplane? The answer is A, low airspeed, high power, high angle of attack. You're going to get that answer on a whole bunch of different questions. Number 3-24. The left turning tendency of an airplane caused by the P factor is a result of B, the propeller blade descending on the right, producing more thrust than the ascending blade on the left. So we covered that. When does P factor cause the airplane to yaw to the left? Answer B, at high angles of attack. So that's the P factor. So high angle of attack is the P factor. Asymmetric propeller loading normally occurs at a high angle of attack. The descending propeller blade on the right side takes a larger bite of the air and produces more thrust than the ascending blade on the left. The result is a left turning tendency of the airplane. Goes toward the weak side. Number 3-26, refer to figure 2. If an airplane weighs 2,300 pounds, what approximate weight would the airplane structure be required to support during a 60-degree bank turn? Well, I already told us 60 degrees is 2 Gs. So we can look at figure 2, but that's just what it's going to tell us. At 60 degrees of bank, the load factor is 2. The wing loading is 2,300 pounds times 2, 4,600 pounds. We can look at figure 2 and see what that looks like. Figure 2, here it is right here. So here's your chart. And so at an angle of attack of 30 degrees, that's the load factor, 1.154. An angle of 60 degrees, it's right there, and it is 2. So you multiply that 2,300 times 2 and get 4,600. 30 degrees, 1.154, which is what I said a while ago. So I think those are the two answers we're going to need. Oh, we're going to need this one too. 45 degrees, 1.414, which you may recognize as the square root of 2. A lot of this has to do with what you would find out with some trigonometric comparisons with what's going on there. All right, so we were down here. So 3-27 is refer to figure 2. If an airplane weighs 3,300 pounds, what approximate weight would the airplane structure be required to support during 30 degrees? Well, that's 3.3 times 1.154, which is 3,810, which is approximately 3,800. So that's what we looked at. If you follow that little red line, it's at 1.154 at 30 degrees. Then let's see here. 3-28, refer to figure 2. If an airplane weighs 4,500 pounds, what approximate weight would the airplane structure be required to support during 45-degree bank turn while maintaining altitude? Well, B, 6,400 pounds, because it's 4,500 times 1.414. That's an amazing thing right there. That's a lot of weight. So that's very concerning. So you got to be careful during your turns. I'm gonna say that for me anyway. I don't want to try to pull the nose up too much or whatever. So the amount of excess load that can be imposed on the wing of an airplane depends on B, the speed of the airplane. The amount of excess load that can be imposed on an airplane depends on its speed. If abrupt control movements or strong gusts are applied to low airspeeds, the airplane stalls before the load becomes excessive. At higher airspeeds, The increased airflow causes a greater lifting capacity. A sudden control input or gust at a high airspeed can result in excessive load factor beyond safe limits. So you can damage the aircraft, such as pull the wings off, which again would be a bad day. 3-30, which basic flight maneuver increases the load factor on an airplane as compared to straight and level flight? Answer is B, turns. In a level turn, lift must be increased to compensate for the loss of a vertical lift and overcome centrifugal force. Because the wings must support not only the airplane's weight, but also the load imposed by centrifugal force, the load factor is greater than 1G. So that's B during turns. 3-31, what force makes an airplane turn? A, the horizontal component of lift. So if you're calculating the vectors of an airplane, the horizontal vector is what controls, it makes the airplane turn. That's not intuitive. In a turn, lift has both a vertical and a horizontal component. The horizontal component of lift, which is also referred to as centripetal force, opposes centrifugal force and causes the airplane to turn. The vertical component of lift opposes gravity and enables the airplane to maintain altitude. So there's some math behind that and some drawings. I bet you that's probably a little bit of controversy because I can see some different ways to look at this, but that's okay. This is what we need to answer for the test and for the check ride and all that good stuff. We have to say it this way. So 3-22 is, let's see, you're nice. Okay. 3-22 is during an approach to a stall, an increased load factor causes the airplane to A, stall at a higher speed. So you got the load factor going, you're in a turn, and the stall speed is higher, and you could stall the aircraft without realizing it's going to stall, and that's concerning. So you'd say, I'm it's not going to stall till I get down to what, 70 or 68 or whatever our stall speed is, and all of a sudden it stalls and you're not there, and you think, crud, what happened? That's what happened. 3-33. What are the 4 flight fundamentals that are involved in maneuvering an aircraft? And it answers C, straight and level flight, turns, climbs, and descents. All control flight consists of one of the 4 fundamental maneuvers: straight and level flight, turns, climbs, descents, or some combination of them. I wrote down load factor. I wanted to study that more. So anything you want to write there, of course, feel free. And of course, next is chapter 4, but that will be a different day and a different try. So I need to know what you think about this, if this is helpful or not. If it is, I'll make some more of them. And if not, well, don't worry about it. Otherwise, if you have questions, let me know. You can drop me a line or contact me on Signal or, texting or email, whatever. So otherwise, have a great, wonderful day. Thank you for watching. Bye.